So there are 4 different types of ECB VAV model Distech devices. This is the ECB CAV example. This is most of the controllers that we're going to have in the field. It's extremely simple. It's power and communication. And this is set up just to chase. We just give it a CFM. We say we want this much flow, and if it's too low, it'll open, and if it's too high, it'll close. That's all it does. Very, very simple. Our next example here is a VAV with power to control a Belimo valve that has hot water running through it. So it's pretty much the same power, comms, and it's going to chase that set point. But where the VAV comes in is it's going to open and close that valve, reacting off of a return duct temperature that is wired directly into that computer. And then this down here is the output to the valve. So it receives a temperature and sends to a Belimo valve to open and close depending on the temperature. Valve is hot water. Yes, there is a cooler. There is, yeah, it's the next one after this one. So this one, it's essentially the same thing, except instead of the temperature, so we do have a temperature probe coming in for the return duct temperature. However, that's going to be ignored. We're going to control the valve based off the temperature that is inside the thermostat. So there's a thermometer inside the thermostat that we're going to use to base the valve position on. And there is a CO2 sensor in the thermostat that, if it's too high, will open all of the air dampers to get the CO2 out of the room.
So in this case, in the previous case, is the control, PID control in the Distech, or is it in Delta V?
Both. There is a Delta V command which overrides the Distech PID, but if we lose comms, the PID will still be active in the Distech controller.
Normal control would be there's the PID in Delta V that's stroking the valve based on.
Yeah, absolutely. However, the carbon is only in Distech. That's if the carbon dioxide is too high. That does not live anywhere in Delta V, to my knowledge. And so, Murray, this is the cooling one. This is our last example of the VAVs. So pretty much the same wiring, power, communication. And then here we have the temperature from the return duct coming in, a cooling valve, Belimo, output going out. And then we also have another output here, which is an SC fan. This is a 0 to 10 volt fan, linear, and the fan starts minimum speed at 2 volts. So this is for the IDF rooms mostly, and this is, I think, only actually. And this is that value is going to be determined by the balancer of the plant. Whenever he gets there, whenever he does this thing, I don't even know what he does, but some magic. This is an ECB 300 example. We have 2 types of the ECB 300 wiring schematics, and the only difference is these 2 wires right here are missing on the other 2. So what this has is I think what order I'm going to go into. So this has, there are 4 ECB 300s, all associated with RL20. The 2 on the ends have temperature probes going into the interstitial area, which is what RL20 controls, and 2 that do not. All 4 of those ECB 300s see those 2 temperatures that are coming into the interstitial area, but only the 2 on the ends actually receive live values from those probes. Everybody else just sees the transfer of that information. There's also a smoke detector associated with each one of these that will shut down everything, get tricked. So it's like a kind of like fuse. And then here's our communication lines coming in here. And then we have the SC fan coming out. That's the command, that's the speed command, works the same as the IDF room. And we have up here is a relay that we send a 12-volt signal to the 12-volt coil. It closes, but we wire a 24-volt common to the other side. And when that closes, we send a signal to a relay. This relay is in series with a damper, and the relay then triggers a fan to start. So it's a hardwired interlock. The damper has to be open for the fan to be able to turn on. And that's due to that relay right there being in series with the damper. And then, like I said, the other wiring schematic, this is missing. But again, all 4 see all of both temperatures. and react in accordance to that. So further down the networking example, we're just going to start at the bottom, work our way up. So each one of these little boxes here is some type of ECB VAV. I don't know what type. I don't know if they're a cooling valve, they're a heating valve, whatever they are. But all of them talk BACnet to through MSTP to this part. All of them are daisy chained together, associated with this part, and this part converts to Ethernet. The Ethernet comes out and talks to, it goes into the switch, comes out, talks to the Rio. Then the Rios come, they go to these switches here, which then is still BACnet all the way through, just Cat6 into the main switch hub here. Then it comes out as BACnet, goes into the Jace. The Jace converts it to Modbus, comes out of the Jace, back into the switch. Then from the switch as Modbus, the PKs can read that. PKs cannot read BACnet, so it's really not a problem. They just won't see that information.